Far out in the depths of space, nearly 10 billion light-years from where we now stand, there exists something that should not exist at all. Something so extreme that when scientists first calculated its properties, they assumed a mistake had been made. They rechecked the numbers. They recalculated the equations. They tested the assumptions again and again. But the mathematics refused to change. What they had discovered was real. A cosmic object so vast, so massive, and so powerful that it challenges our understanding of what nature is capable of creating. An object that formed when the universe itself was still young, chaotic, and violent. A relic from an era when galaxies were still assembling, when gravity ruled unchecked, and when the cosmos was far more hostile than it is today. This is the story of TON 618. At the heart of this distant beacon lies a black hole containing roughly 66 billion times the mass of our Sun. Not millions. Not billions. 66 billion. If this black hole were placed where our Sun currently sits, its event horizon would stretch far beyond the orbit of Pluto, extending nearly 40 times farther than the edge of our solar system. And yet, despite being nearly 10 billion light-years away, it shines with the power of over 100 trillion suns. When the light we see today began its journey toward Earth, our planet did not yet exist. The Sun had not yet ignited. Even the Milky Way was still in its formative stages. The universe was barely a quarter of its current age. To understand what this object truly represents, we must begin not at its center, but here, at home. The faint band of light stretching across the night sky is the Milky Way, our galaxy. Within it are hundreds of billions of stars, arranged in a graceful spiral held together by gravity. Near the center of this vast structure lies Sagittarius A*, a supermassive black hole containing about 4 million solar masses. It anchors the rotation of our entire galaxy. By any everyday standard, it is enormous. But compared to what we are about to encounter, it is insignificant. The object we seek is not in this galaxy. Not in our local group of galaxies. Not even remotely nearby. To reach it, we must leave behind every star visible to the naked eye. We must travel beyond the Milky Way's satellite galaxies. Past the Magellanic Clouds, and beyond Andromeda, the massive spiral galaxy destined to collide with our own in roughly 4 billion years. We continue outward. Galaxies multiply in every direction. Dozens become hundreds. Hundreds become thousands. Each one contains hundreds of billions of stars. Each star may host planets. Each planet carries the possibility, however small, of life. And yet, across all this immensity, we have never detected a single confirmed signal from another civilization. Perhaps we are alone. Or perhaps the universe is simply too vast for civilizations to ever find one another across the cosmic void. Eventually, we enter true intergalactic space. Regions so empty that you could travel millions of light-years without passing a single star. Here, the temperature hovers just above absolute zero, warmed only by the faint afterglow of the Big Bang itself. The darkness feels complete. But it does not last. Points of light begin to appear, scattered at first, then multiplying until they fill the sky in every direction. These are galaxies, organized not randomly, but into vast filaments and sheets forming a cosmic web. Immense voids stretch between them, while gravity pulls matter into dense knots along invisible rivers of dark matter. As we travel farther, we are also traveling backward in time. Nearby galaxies appear mature and orderly, their star formation slowing. But the farther we go, the younger and more chaotic galaxies become. We see frequent mergers, intense bursts of star formation, and distorted shapes sculpted by gravitational encounters. This is cosmic history unfolding before our eyes. Ahead, one object begins to outshine all the others. At first, It looks like a star. But it is no star. It is a quasar, a cosmic lighthouse powered by a feeding supermassive black hole. When quasars were first discovered in the early 1960s, astronomers believed they were strange stars within our own galaxy. They appeared point-like, even in powerful telescopes. But when their spectra were analyzed, something astonishing emerged. The familiar fingerprints of elements like hydrogen were shifted dramatically toward redder wavelengths. This redshift revealed that these objects were racing away from us at incredible speeds, implying they were billions of light-years distant. According to the expansion of the universe, this meant they had to be unimaginably luminous, more luminous than entire galaxies. Yet all that energy was coming from regions no larger than our solar system. The only explanation was extraordinary. These objects were powered by supermassive black holes devouring enormous quantities of matter. As gas spirals inward through an accretion disk, friction and magnetic forces heat it to extreme temperatures. Before crossing the event horizon, the matter radiates vast amounts of energy across the electromagnetic spectrum. Ton 618 was first catalogued in 1957 at the Tonantzintla Observatory in Mexico. At the time, it appeared unremarkable, a single blue point among thousands. For decades, it remained largely ignored. But as observational technology improved, astronomers began to realize that this object was different. Very different. The black hole at its center was not merely supermassive. It was ultramassive, one of the largest ever discovered. As we approach, the quasar resolves from a point of light into a vast, turbulent structure. Surrounding the black hole is an enormous accretion disk, stretching thousands of astronomical units across. This disk is a swirling maelstrom of doomed matter, divided into regions with dramatically different physical conditions. In the outer regions, far from the black hole's strongest grip, temperatures are relatively modest, only a few thousand degrees. Gas orbits at hundreds of kilometers per second, still mostly neutral and only weakly ionized. But moving inward, gravity tightens its hold. Orbital speeds increase into the thousands of kilometers per second. Friction between faster inner material and slower outer material converts motion into heat. Temperatures rise to hundreds of thousands, then millions of degrees. At this point, atoms are stripped apart into plasma, bare nuclei and free electrons threaded by intense magnetic fields. These magnetic fields play a crucial role. They transport angular momentum outward, allowing matter to spiral inward. Without them, the gas would simply orbit forever, unable to fall into the black hole. Closer still, conditions become almost beyond comprehension. Temperatures exceed billions of degrees. Matter moves at significant fractions of the speed of light. Relativistic effects dominate. Time slows. Space warps. The rotating black hole drags spacetime itself along with it. This is the innermost stable orbit, the final region where matter can circle the black hole without falling in. Any small disturbance sends material plunging past the event horizon within hours or days, radiating its final energy in intense bursts of X-rays and gamma rays. The total power output is staggering. Across all wavelengths, TON 618 emits roughly 4 times 10 to the 40th watts. If this quasar were placed at the distance of Alpha Centauri, it would appear 10,000 times brighter than our Sun does from Earth. The radiation would strip away oceans, atmosphere, and life itself in a matter of hours. Yet all this energy comes from a simple principle. Mass and energy are equivalent. Einstein's equation, E equals mc squared, reveals that even small amounts of mass contain enormous energy. Black hole accretion is one of the most efficient energy conversion processes in the universe. Up to 40% of the infalling mass's rest energy can be radiated away before crossing the event horizon. Ton 618 consumes the equivalent. of 20 to 30 suns every year. And yet, compared to its immense mass, this growth is almost negligible. At that rate, it would take billions of years to double in size. Which raises an extraordinary question. How did something this massive form so early in the universe's history? That question remains one of the greatest mysteries in astrophysics. The light we receive from this quasar began its journey when the universe was only about 3.2 billion years old. The Big Bang had occurred 13.8 billion years ago, which means this black hole had less than a quarter of the universe's current lifetime to reach a mass of 66 billion suns. That alone should not be possible. The first stars likely formed within the first 1 to 200 million years after the Big Bang. These earliest stars, composed almost entirely of hydrogen and helium, lived fast and died young. Many collapsed directly into black holes with masses perhaps tens or hundreds of times that of the Sun. These were the seeds. But growing from a seed of 100 solar masses to 66 billion within 3 billion years requires growth at the absolute limits allowed by physics. Black holes grow by accretion, but accretion is self-limiting. As matter falls inward, it heats up and emits radiation. That radiation pushes back against infalling material. When radiation pressure balances gravity, accretion reaches what is known as the Eddington limit. Beyond this rate, infalling gas is blown away. A black hole accreting steadily at the Eddington limit grows exponentially, doubling its mass roughly every 50 million years. Starting with 100 solar masses, it could theoretically reach billions of solar masses within a billion years. In the most optimistic scenario, it could even reach tens of billions within 3 billion years. But this requires uninterrupted feeding. In reality, black holes experience feast and famine. Fuel supplies vary. Accretion disks become unstable. Gas clouds fragment. Mergers disrupt inflows. Maintaining near-continuous Eddington accretion for billions of years is extraordinarily difficult. There is also the matter of supply. To grow to 66 billion solar masses, the black hole must consume an enormous fraction of an entire galaxy's baryonic matter. Gas must lose angular momentum and flow inward rather than settling into stable orbits. This is not trivial. Several mechanisms may have worked together to produce such an extreme object. One possibility is that the black hole did not start small. In the early universe, vast clouds of pristine hydrogen and helium may have collapsed directly into black holes without first forming stars. If cooling was suppressed, perhaps by intense ultraviolet radiation from nearby star-forming regions, these clouds could avoid fragmentation. Such direct collapse black holes might begin life with masses of 10,000 to 100,000 suns, providing a significant head start. Another possibility is that accretion occasionally exceeded the Eddington limit. In thick, puffed-up accretion flows, radiation can become trapped and carried inward with the gas rather than escaping to push back. This allows brief episodes of super-Eddington accretion, where black holes grow faster than normally allowed. Galaxy mergers likely played a critical role as well. In the early universe, galaxies were closer together and far more gas-rich. Collisions and mergers were common. When galaxies merge, gravitational torque strips angular momentum from gas clouds, funneling enormous quantities of matter toward the central regions. The black holes at the centers of merging galaxies eventually spiral together and merge themselves, rapidly increasing mass in single events that release tremendous energy in gravitational waves. The early universe also provided abundant fuel. Most baryonic matter had not yet been locked into stars. Hydrogen and helium gas filled galaxies, making it far easier for black holes to feed. The most likely explanation is not a single mechanism, but a combination. Massive initial seeds, episodes of rapid accretion, frequent mergers, and exceptionally favorable environments all working together. TON 618 represents an extreme outcome of these processes. It is exceptional, but it is not unique. Across the distant universe, astronomers have identified tens of thousands of quasars powered by supermassive black holes. Nearly all of them are seen at great distances, meaning we observe them as they existed billions of years ago. In the nearby universe, quasars are rare. Most supermassive black holes today are quiet and starved, including the one at the center of our own galaxy. This tells us something profound about cosmic history. There was a time, roughly 1 to 4 billion years after the Big Bang, when quasar activity peaked. During this era, quasars were perhaps 100 times more common than they are today. This was the universe's most violent and energetic phase. The reasons are clear. Young galaxies were gas-rich. Mergers were frequent. Fuel was abundant. Black holes fed rapidly and shone brilliantly. But this activity could not last. As quasars shine, they affect their surroundings. Intense ultraviolet and X-ray radiation heats nearby gas, preventing it from cooling and collapsing to form stars or feed the black hole. Radiation pressure pushes gas outward in powerful winds. In some systems, narrow jets of matter erupt from the black hole's poles at near light speed, plowing through the surrounding medium and inflating enormous bubbles of hot plasma. This feedback is self-regulating. As the black hole grows more massive and luminous, its output eventually disrupts its own fuel supply. Accretion slows. The quasar fades. Star formation declines. The galaxy settles into a quieter state. TON 618 is observed near the peak of this quasar era, when the universe was roughly 3.2 billion years old. We see it in its glory days, shining near its maximum possible luminosity. If we could observe it as it exists today, more than 10 billion years later, it would likely appear very different. The quasar has almost certainly faded. The black hole may have grown somewhat larger through continued accretion and mergers, but it is probably no longer actively feeding at high rates. It likely resides at the center of a massive elliptical galaxy filled with ancient red stars, its violent youth long behind it. This raises another remarkable question. How do we know how massive this black hole is? At a distance of 10 billion light-years. We cannot track individual stars orbiting it as we do for Sagittarius A star. Instead, astronomers rely on indirect but powerful techniques. One of the most important is reverberation mapping. Quasar brightness varies over time as accretion flows fluctuate. When the central accretion disk brightens, nearby clouds of gas respond after a delay, glowing as they are ionized by the increased radiation. This region, known as the broadline region, emits strong spectral lines that are Doppler broadened by the gas's high velocities. By measuring the time delay between changes in the disks, light and the response of the surrounding gas, astronomers can estimate the size of the broadline region. By measuring the width of the spectral lines, they can determine the velocity of the gas. Combining size and velocity yields the mass of the central black hole through the laws of gravity. For very distant quasars, astronomers also use empirical relationships between luminosity and broadline region size, calibrated from closer systems where reverberation mapping has been performed directly. Multiple independent methods converge on the same conclusion. The black hole in TON 618 has a mass of roughly 66 billion solar masses, with uncertainties perhaps a factor of 2 or 3 in either direction. Even at the low end, it remains one of the most massive black holes ever discovered. Another check comes from the Eddington limit itself. The luminosity of TON 618 requires a minimum black hole mass of tens of billions of solar masses to avoid blowing away its accretion flow. The observed brightness places it at roughly half to two-thirds of its Eddington limit, an extreme but physically reasonable value. Now, imagine approaching this object. From several light-years away, the quasar already dominates the sky, far brighter than any star. Radiation levels are lethal without heavy shielding. High-energy photons ionize atoms and damage. Electronics. At 1 light-year, the quasar's intensity rivals sunlight at Earth, but with a spectrum rich in ultraviolet and X-rays. Space itself is filled with ionized plasma, heated to millions of degrees by the relentless radiation. Closer still, the quasar's structure becomes visible. The accretion disk spreads across the sky, glowing in bands of red, yellow, white, and blue as temperature increases inward. Bright flares erupt where magnetic fields reconnect, releasing stored energy in violent bursts. At light-month distances, relativistic effects dominate the view. The side of the disk rotating toward us appears dramatically brighter due to Doppler boosting and relativistic beaming. Light from the far side of the disk bends around the black hole, forming a luminous ring. We see multiple images of the same regions of space distorted by gravity. At the innermost stable orbit, matter races around at significant fractions of the speed of light. Time itself behaves differently here. Orbits take hours or days. Any disturbance sends matter plunging inward, releasing its final energy before vanishing forever. Then we reach the event horizon. For this black hole, the event horizon spans roughly 1,300 astronomical units. Light would take nearly 6 weeks to travel around its circumference. It is not a physical surface, but a boundary in spacetime. Beyond it, all future paths lead inward. Crossing the horizon is uneventful. There is no sudden sensation. No barrier. From the falling observer's perspective, nothing special happens. But once crossed, escape becomes impossible. Inside, spacetime itself carries everything toward the singularity. Tidal forces slowly increase. At first they are survivable. But deeper in, they grow relentless. Stretching, compressing, tearing. Eventually, matter is pulled apart atom by atom, particle by particle. This is spaghettification. For an ultramassive black hole, the journey from horizon to singularity may take hours or even days of subjective time. Larger black holes have gentler tidal forces near their horizons, prolonging the fall. But the end is inevitable. At the singularity, general relativity predicts infinite density and infinite curvature. Physics breaks down. Our theories no longer apply. We do not know what truly happens there. And that ignorance is not a failure. It is an invitation. The singularity represents the boundary of our understanding. According to general relativity, it is a point where spacetime curvature becomes infinite, where density diverges without limit, and where the equations that have so successfully described gravity everywhere else collapse into meaningless infinities. This is not merely a mathematical inconvenience. It is a clear signal that our current theories are incomplete. To describe what truly happens at the center of a black hole, we would need a theory that unifies general relativity with quantum mechanics. A theory of quantum gravity. Despite decades of effort, no such theory has yet been experimentally confirmed. Candidates like string theory and loop quantum gravity offer possible resolutions, suggesting that the classical singularity might be replaced by something finite but extreme, or perhaps by an entirely different structure that prevents true infinities from forming. For now, the singularity remains a mystery. But even without understanding the deepest interior, the existence of an ultramassive black hole like the one in TON 618 has profound implications. It serves as a natural laboratory for testing physics under conditions impossible to recreate on Earth. Near this object, gravity is stronger and spacetime curvature more extreme than almost anywhere else accessible to observation. The behavior of light, matter, and time in this environment allows astronomers to test predictions of general relativity in regimes far beyond those available in our solar system. So far, every observation is consistent with Einstein's theory. Light bends exactly as predicted. Gravitational redshift matches expectations. Relativistic effects in accretion disks follow the equations with remarkable precision. Even in these extreme conditions, general relativity continues to hold. At the same time, the very existence of this black hole challenges our understanding of cosmic structure formation. Growing an object of this size so early in the universe's history pushes models of black hole growth, galaxy evolution, and gas dynamics to their limits. It forces astronomers to refine theories of accretion, feedback, and mergers, not just for this single object, but for the entire population of massive galaxies. Black holes do not grow in isolation. Observations reveal tight correlations between the mass of a central black hole and properties of its host galaxy, such as the mass of the stellar bulge and the velocity. Dispersion of stars. These relationships suggest that black holes and galaxies evolve together, their growth tightly linked through shared gas supplies and feedback processes. For a black hole of 66 billion solar masses, these correlations imply a host galaxy of extraordinary size. The stellar bulge alone would contain hundreds of billions of solar masses worth of stars, placing it among the most massive galaxies in the early universe. Observations support this picture. At wavelengths where the quasar's glare is less dominant, astronomers detect emission from dust, heated by intense star formation throughout the host galaxy. The inferred star formation rate is enormous, possibly hundreds or even thousands of times greater than that of the Milky Way today. This is a galaxy in the midst of a violent growth phase, rapidly converting gas into stars while simultaneously feeding its central black hole. These processes are not independent. The same gas that fuels star formation also feeds the black hole. And the energy released by the black hole profoundly affects the galaxy in return. Radiation pressure from the quasar drives powerful winds that can expel gas from the galaxy's central regions. Ultraviolet and X-ray radiation ionizes vast volumes of gas, heating it and preventing further collapse. If jets are present, they inject mechanical energy into the surrounding medium, carving out enormous cavities and heating gas on scales larger than the galaxy itself. This feedback regulates growth. Without it, massive galaxies would continue forming stars at extreme rates, growing far larger than observed. Instead, feedback eventually shuts down both star formation and black hole accretion, leaving behind massive, quiescent elliptical galaxies dominated by ancient stars. TUN 618 is likely caught during the brief but spectacular phase when this regulation is still underway. The black hole shines brilliantly, but in doing so, it sows the seeds of its own dormancy. Over tens to hundreds of millions of years, gas supplies will be exhausted or expelled. Star formation will decline. The quasar will fade. The galaxy will age. Billions of years later, what remains will be a giant elliptical galaxy, filled with old, red stars, its central black hole. Quiet but still immense. A relic of a more violent cosmic epoch. Understanding how astronomers study an object so distant requires appreciating the ingenuity of modern observational astronomy. TUN 618 lies 10 billion light-years away. The photons reaching our telescopes today have traveled for 10 billion years, passing through expanding space, absorbing the imprint of every intervening structure. Extracting information from such ancient, faint light is a remarkable achievement. Ground-based optical and infrared telescopes play a critical role. Facilities like the Keck telescopes in Hawaii use segmented mirrors 10 meters across to collect enormous amounts of light. Each mirror consists of dozens of precisely aligned segments acting as a single surface. In Chile, the Very Large Telescope operates 4 8-meter telescopes that can work independently or together to achieve higher resolution. In Spain, the Gran Telescopio Canarias boasts the largest single-aperture optical mirror currently in operation. These telescopes are equipped with sophisticated spectrographs that disperse light into its component wavelengths. By analyzing spectra. Astronomers can identify chemical elements, measure temperatures and densities, and determine velocities through Doppler shifts. From subtle distortions in spectral lines, they infer conditions in regions they can never directly observe. Space-based observatories provide crucial complementary data. Above Earth's atmosphere, telescopes avoid atmospheric distortion and absorption. Ultraviolet and X-ray wavelengths, blocked at the surface, become accessible. The Hubble Space Telescope, despite its relatively modest mirror, has provided invaluable observations of distant quasars. By capturing light that was emitted in ultraviolet wavelengths and redshifted into the visible range, the James Webb Space Telescope extends this capability into the infrared. With its large, segmented mirror and cryogenic design, it can detect faint infrared emission from the host galaxies of distant quasars, allowing astronomers to study star formation and galactic structure that would otherwise be hidden by the quasar's glare. X-ray observatories probe the hottest regions of the accretion disk. These telescopes detect radiation emitted by gas at billions of degrees near the black hole's inner edge. From the shape of iron emission lines distorted by relativistic effects, astronomers infer black hole spin and test general relativity in the strongest gravitational fields. Accessible. Radio and millimeter observatories reveal yet another layer. Arrays like the Very Large Array and ALMA combine signals from many antennas to achieve resolution equivalent to enormous single dishes. These facilities map cold molecular gas, tracing the fuel for both star formation and black hole accretion. They reveal how gas flows through galaxies and how feedback reshapes the interstellar medium. All of this data must be carefully calibrated, processed, and interpreted. Raw observations are converted into scientific measurements through complex pipelines that correct for instrumental effects, atmospheric interference, and cosmic noise. Astronomers then compare observations with theoretical models and numerical simulations, refining both in an iterative process that gradually improves understanding. Despite these efforts, many questions remain open. How exactly did the first black hole seeds form? How common were direct collapse black holes in the early universe? How often did super-Eddington accretion occur? What role did mergers play in assembling the most massive black holes? Is there an upper limit to black hole mass? Some theoretical work suggests that feedback processes impose a practical ceiling, perhaps around 100 to 200 billion solar masses. Beyond this, radiation pressure and mechanical feedback may become so effective that further growth is suppressed. Ton 618 lies tantalizingly close to this possible limit, making it a key object for exploring the extremes of gravity. The black hole's spin remains another major unknown. Spin influences accretion efficiency, jet production, and energy extraction. Prolonged accretion tends to spin black holes up, while chaotic accretion and mergers can reduce or randomize spin. Measuring spin in distant quasars is extraordinarily challenging, requiring detailed X-ray spectroscopy at the limits of current technology. And then there is the deepest mystery of all. What happens to information that falls into a black hole? Quantum mechanics forbids true information loss, yet classical descriptions of black holes seem to erase information at the singularity. This apparent contradiction, known as the black hole information paradox, has driven decades of debate and theoretical innovation. Proposed resolutions range from information being encoded in Hawking radiation to radical modifications of spacetime near the event horizon. None have yet been definitively confirmed. These are not abstract puzzles. They strike at the heart of fundamental physics. Solving them would reshape our understanding of reality itself. The future of black hole research promises to deepen these mysteries rather than immediately resolve them. But in doing so, it will bring us closer to understanding the universe at its most fundamental level. Objects like the black hole in TON 618 serve as signposts, pointing toward the limits of our theories and guiding the development of new ones. One of the most transformative tools in this effort is the study of gravitational waves. For centuries, astronomy relied entirely on light. Visible light, radio waves, X-rays, gamma rays, all are different forms of electromagnetic radiation. But gravity itself carries information, and until recently, humanity had no way to detect it directly. That changed in 2015, when the LIGO Observatory detected ripples in spacetime produced by the merger of two stellar mass black holes. That single detection opened an entirely new window on the universe. Gravitational waves allow us to observe events that produce little or no light. They carry unaltered information about the motion of massive objects, unaffected by dust, gas, or intervening matter. For black hole mergers, they provide a direct measurement of mass, spin, and energy release. So far, detectors like LIGO and Virgo are sensitive primarily to mergers of stellar mass black holes and neutron stars. But in the coming decades, this will change dramatically. The Laser Interferometer Space Antenna, known as LISA, is a planned space-based gravitational wave observatory consisting of 3 spacecraft arranged in a vast triangular formation millions of kilometers across. Free from seismic noise and Earth's gravity, LISA will be sensitive to much lower frequency gravitational waves than ground-based detectors. These frequencies are precisely those produced by supermassive black hole mergers. With LISA, astronomers expect to observe the inspiral and merger of black holes with millions to billions of solar masses across much of the observable universe. Such observations will provide direct measurements of black hole masses and spins, test general relativity in extreme regimes, and reveal how often massive black holes merge during galaxy evolution. Although a merger involving a black hole as massive as TON 618 would be extraordinarily rare, LISA could detect mergers involving its progenitors or its descendants. Each detection would add a crucial piece to the puzzle of how such extreme objects assemble over cosmic time. Gravitational waves also offer a way to probe the early universe. Some theories predict that primordial black holes may have formed directly from density fluctuations shortly after the Big Bang. While these would likely be much smaller than TON 618, their existence could influence structure formation and potentially provide seeds for later growth. Detecting or constraining such populations would have profound implications for cosmology. Meanwhile, electromagnetic observations will continue to advance. Next-generation ground-based telescopes like the extremely large telescope in Chile, with a primary mirror nearly 40 meters across, will collect unprecedented amounts of light. These instruments will resolve fine details in distant galaxies and measure spectra with extraordinary precision. They will allow astronomers to study the environments of quasars like TON 618 in greater detail than ever before. At radio wavelengths, upgrades to existing arrays and the eventual completion of the square-kilometer array will map cold gas across cosmic time, revealing how galaxies acquire, lose, and recycle the material that fuels star formation and black hole growth. Together, these tools will transform objects that once appeared as single points of light into richly detailed systems. And yet, even as our observational capabilities improve, the deepest questions remain conceptual. What is the true nature of spacetime? General relativity describes gravity as the curvature of spacetime caused by mass and energy. Quantum mechanics describes the behavior of particles and fields on the smallest scales. Both theories are extraordinarily successful within their domains, yet they are fundamentally incompatible in their current forms. Black holes lie at the intersection of these theories. At their horizons, quantum effects may play subtle but important roles. At their centers, classical descriptions break down entirely. Understanding black holes is therefore inseparable from understanding the fundamental structure of reality. TON 618, by virtue of its sheer scale, amplifies these issues. Its event horizon is vast. Enough that tidal forces at the boundary are relatively gentle. An observer crossing it would not be torn apart immediately. Yet the interior still leads inevitably to a region where known physics fails. The contrast between the calm crossing and the violent end highlights the limitations of intuition shaped by everyday experience. There is also a deeper, more philosophical dimension. This black hole existed when the universe was young. It grew rapidly, shone brilliantly, and then likely faded into quiet obscurity. For billions of years, it has persisted, almost unchanged. While galaxies formed, stars lived and died, and planets came and went. Its lifespan dwarfs that of any civilization. From a cosmic perspective, even the entire history of humanity is a brief flicker. The rise and fall of cultures, the building of cities, the exploration of space, all unfold in a time span insignificant compared to the age of this object. And yet, through the application of mathematics, physics, and technology, we have come to know it. We have measured its mass. We have estimated its size. We have traced the light from its accretion disk across 10 billion years of cosmic expansion. We have inferred the processes that built it and the role it played in shaping its host galaxy. This is one of humanity's greatest achievements. Without leaving Earth, without ever approaching this object directly, we have reconstructed its story from faint photons captured by mirrors and detectors. We have turned points of light into physical understanding. In doing so, we have also learned something about ourselves. The same laws of physics that govern the fall of an apple shape the growth of galaxies and the behavior of black holes. The universe is not arbitrary. It is structured, lawful, and intelligible, even at its most extreme. Ton 618 is not a monster in the sense of something unnatural or aberrant. It is the result of gravity operating patiently and relentlessly over billions of years. Given enough time, enough matter, and the right conditions, the universe produces objects of astonishing scale and power. Somewhere, in the vastness of space, there may exist black holes even larger, even more massive, perhaps waiting to be discovered. Or perhaps TON 618 lies near the ultimate limit. A boundary beyond which growth becomes impossible. We do not yet know. What we do know is that this object, shining from the depths of cosmic time, connects us to the early universe. It reminds us that the cosmos is dynamic, evolving, and far stranger than our ancestors ever imagined. And as we continue to look deeper into space and further back in time, objects like this will continue to challenge our understanding, refine our theories, and expand our sense of what is possible. In the end, the black hole in TON 618 is not just a curiosity. It is a message from the universe itself, a reminder of the immense scales on which reality operates, and of the extraordinary capacity of the human mind to comprehend them. To truly grasp the scale of what TON 618 represents, it helps to step back from numbers and equations and consider perspective. Human intuition is built for survival on a small planet, under a single star, within a narrow slice of reality. Our senses evolved to judge distances measured in meters, speeds measured in seconds, and timescales measured in years. Black holes like this exist far outside those boundaries. If the history of the universe were compressed into a single calendar year, TON 618 would appear in early April. Earth would not form until early September. Complex life would not emerge until mid-December. All of recorded human history would unfold in the final few seconds before midnight on December 31st. And yet, from those final seconds, we look back across the entire year and reconstruct. What happened? The photons that carry the story of TON 618 have crossed expanding space for 10 billion years. During that journey, the universe itself stretched beneath them. Wavelengths lengthened. Energies diminished. Entire galaxy clusters moved apart. Still, those photons survived, each one preserving a fragment of information about the conditions that created it. In a sense, observing a distant quasar is a form of time travel. We are not seeing TON 618 as it is now. We are seeing it as it was, long before our planet existed. The object may have changed dramatically since then. Its quasar phase may have ended billions of years ago. Its host galaxy may have merged with others, reshaped by cosmic evolution. But the light arriving today freezes one moment forever. This is one of the most profound aspects of astronomy. The sky is not a snapshot of the present. It is a layered archive of the past, with distance translating directly into time. Every direction we look reveals a different era of cosmic history. TON 618 occupies a particularly important chapter in that history. The epoch when it shone brightly was a turning point. The universe was transitioning from a chaotic, rapidly evolving state into a more structured and mature one. Galaxies were growing, black holes were reaching enormous masses, and feedback processes were beginning to regulate further growth. In many ways, this era determined the large-scale structure of the universe we see today. If black holes had grown faster or more efficiently, feedback might have suppressed star formation more strongly, leaving a darker, emptier cosmos. If they had grown more slowly, galaxies might have become overly massive and unstable. The balance we observe suggests a delicate interplay between gravity, radiation, and gas dynamics. TON 618 represents one extreme of that balance. Studying extremes is often the fastest way to understand limits. Just as studying the fastest particles revealed the structure of matter, studying the largest black holes reveals the structure of cosmic evolution. These objects push theories to their breaking points, exposing weaknesses and guiding refinement. There is also a quiet irony in the nature of black holes. They are defined by absence. They emit no light of their own. They reveal themselves only through their influence on surroundings. And yet, the brightest objects in the universe, quasars, are powered by them. Darkness fuels brilliance. Absence creates visibility. This paradox runs deep. The black hole consumes matter, yet in doing so, it illuminates the universe. The very act of destruction becomes a source of information. Without accretion disks, without infalling gas heating to extreme temperatures, black holes would remain nearly invisible. We would suspect their existence, but know little about their properties. TON 618 is visible precisely because it is feeding. This raises another subtle point. Black holes are often portrayed as cosmic vacuum cleaners, endlessly swallowing everything around them. In reality, they are remarkably inefficient at capturing matter. Gas must lose enormous amounts of angular momentum to fall inward. Most matter that approaches a black hole does not fall in directly. It orbits, heats up, radiates, and often gets blown away before ever crossing the horizon. The immense luminosity of TON 618 is not evidence of unstoppable consumption, but of intense resistance. Matter struggles against gravity, sheds energy, and only gradually succumbs. Even at its peak, the black hole consumes a tiny fraction of the available matter in its host galaxy. This reframes the black hole not as a destroyer, but as a regulator. By limiting its own growth through feedback, it shapes the future of its galaxy. By expelling gas, it suppresses star formation. By heating its environment, it changes the thermodynamic state of intergalactic space. In this way, black holes act as architects of cosmic structure. They help determine which galaxies remain active and which become dormant. They influence the distribution of elements forged in stars. They affect the temperature and density of gas on scales far larger than themselves. TON 618, despite being just one object among trillions, participates in this grand pattern. There is also a lesson here about scale and humility. From our perspective, Earth feels vast. Mountains seem permanent. Oceans appear endless. Civilizations rise and fall, leaving traces that endure for millennia. But on cosmic scales, planets are dust motes. Stars are sparks. Galaxies are transient patterns in an expanding medium. Black holes endure. Once formed, they are extraordinarily long-lived. The only known mechanism for their evaporation is Hawking radiation, a quantum effect so weak that even stellar mass black holes will persist for timescales far exceeding the current age of the universe. For supermassive black holes like TON 618, evaporation times are incomprehensibly long, on the order of 10 to the power of 100 years or more. This is longer than the era of stars, longer than the era of galaxies, longer than almost any structure we can imagine. In the far future, when stars have burned out and galaxies have faded, black holes may be among the last remaining macroscopic objects. They will quietly lose mass, particle by particle, over eons, until they finally disappear in faint bursts of radiation. TON 618 will outlast not only humanity, but likely the Milky Way itself. Yet here we are, fragile beings on a small planet, capable of understanding it. That contrast is worth lingering on. The universe did not evolve with the intention of being understood. The laws of physics operate blindly, without purpose or awareness. And yet, those same laws give rise to minds capable of reflection, curiosity, and comprehension. TON 618 is not just an object of study. It is a testament to the reach of human thought. By following light across 10 billion years, by interpreting subtle shifts in spectral lines, by applying abstract mathematics to distant phenomena, we have bridged a gap that seems, at first glance, impossible to cross. In doing so, we have expanded the boundaries of our world. And perhaps that is the deeper meaning of studying objects like this. Not simply to catalog extremes, or to test equations, but to place ourselves within a much larger story. To recognize that we are part of a universe capable of producing both ultramassive black holes and conscious observers. To see that understanding is itself a natural consequence of the same processes that shape stars and galaxies. As long as there are minds willing to ask questions, objects like TON 618 will continue to matter. They will continue to inspire awe, challenge assumptions, and remind us that reality is far larger, deeper, and more subtle than it appears from the surface of a small world orbiting an ordinary star. And somewhere, far beyond our reach, the remnants of this ancient quasar continue their silent journey through time, unchanged, patient, and indifferent, while the light it once emitted carries its story forward, waiting to be understood. There is one final layer to this story that often goes unspoken, not because it is unimportant, but because it sits at the intersection of science and meaning. TON 618 forces us to confront not only the limits of physics, but the limits of perspective. From a purely physical standpoint, this black hole is an inevitable consequence of gravity. Given enough mass, enough time, and the right conditions, space-time curves inward on itself and creates a region from which nothing can escape. No intention is required. No design. Just the quiet, relentless operation of natural law. And yet, when we describe it, we cannot help but reach for language that feels almost mythic. We speak of event horizons, of points of no return, of singularities hidden behind veils of darkness. We imagine falling inward, time stretching, light bending, reality warping. These images resonate because they echo something deeply human. The idea of boundaries, of thresholds beyond which knowledge fails. TON 618 sits at such a threshold. It marks the edge of what we can currently test and verify. Beyond its horizon lies a region we can describe mathematically, but never observe directly. No signal can cross back to us. In this sense, black holes introduce a fundamental asymmetry into the universe. There are events that occur that matter in a physical sense, but that are forever removed from observation. This challenges a deeply held assumption. For centuries, science has operated under the belief that, in principle, everything that happens in the universe can be observed or inferred given enough time and the right tools. Black holes complicate that belief. They create permanent blind spots in reality. And yet, those blind spots do not render the universe unknowable. Instead, they force us to be precise about what knowledge means. We learn not by seeing everything, but by understanding the rules that govern what can and cannot be seen. The event horizon becomes not just a physical boundary, but an epistemological one. What we know is constrained, but not arbitrary. TON 618 also reshapes how we think about scale and significance. In human terms, size often correlates with importance. Larger structures feel more consequential. But the universe does not share this bias. A single subatomic particle follows the same fundamental rules as the largest black hole. A quantum fluctuation in the early universe can influence the distribution of galaxies billions of years later. TON 618 is enormous, but it is not central. It does not occupy a special location. It is not at the center of the universe. It is not unique in kind. It is one realization among many of what gravity can produce. This realization is strangely liberating. It means the universe is not built around extremes or exceptions, but around consistency. The same principles apply everywhere. At all times, regardless of scale. Understanding grows not from discovering special cases, but from recognizing patterns that repeat across vastly different contexts. There is also the question of inevitability. Given the laws of physics as we understand them, was the formation of an object like TON 618 unavoidable? Or was it the product of an extraordinarily rare chain of events? The answer may be both. On one hand, gravity ensures that some regions will always collapse more efficiently than others. On the other, reaching such an extreme mass likely required a convergence of favorable conditions: early formation, abundant fuel, frequent mergers, and sustained accretion. This suggests that while TON 618 is rare, it is not miraculous. Rarity does not imply violation of natural law. It implies sensitivity to initial conditions. In that sense, TON 618 is a cosmic outlier, but not an anomaly. It represents the tail end of a distribution, not a breakdown of physics. This distinction matters. Because when we encounter objects at the extremes, our instinct is often to treat them as exceptions that require special explanations. Sometimes they do. But more often, they reveal the full range of what existing processes can produce when given enough time and opportunity. Black holes teach this lesson repeatedly. From stellar mass black holes, formed by collapsing stars, to supermassive black holes anchoring galaxies, to ultramassive black holes like TON 618, the underlying physics remains the same. Only the scale changes. This continuity is one of the most beautiful aspects of physics. It means that understanding does not fragment as we move outward in scale. It deepens. The same equations that describe the orbit of planets also describe the motion of gas in accretion disks. The same principles that govern energy conservation in a laboratory apply to quasars billions of light-years away. There is no separate set of rules for the distant universe. TON 618 obeys the same laws as everything else. This has implications beyond astrophysics. It suggests that the universe is not only vast, but coherent. That complexity arises not from chaos, but from the repeated application of simple rules across immense spans of time and space. In that coherence lies the possibility of understanding. As we look ahead, the study of black holes will continue to evolve. New instruments will refine measurements. New theories will attempt to unify gravity and quantum mechanics. Some ideas will fail. Others will survive. Progress will be uneven, and certainty will remain elusive. But objects like TON 618 will remain anchors. They will continue to provide benchmarks against which theories are tested. They will continue to inspire new questions. And they will continue to remind us that the universe is capable of producing structures far beyond the scale of everyday experience. In the end, the story of TON 618 is not about fear or destruction. It is about possibility. The possibility that the universe, through the blind operation of natural law, can generate extremes of mass and energy. The possibility that minds like ours can arise within that universe and reconstruct its history. The possibility that understanding, however incomplete, is achievable. Somewhere in the depths of space, the remnant of this ancient quasar persists. Silent. Immense. Unconcerned with being known. And yet, here we are, telling its story. Not because the black hole demands it, but because curiosity does. There is a subtle but important shift that happens when we spend enough time with an object like TON 618. At first, it feels alien. Distant. Abstract. A collection of numbers too large to truly grasp. But gradually, as the story unfolds, it becomes something else. Not familiar in a personal sense, but intelligible. Governed. Connected. And that shift matters. Because understanding does not require closeness. It requires structure. It requires that reality behaves consistently enough for patterns to emerge. TON 618 demonstrates that even at the most extreme scales, the universe remains lawful. This realization reshapes how we think about uncertainty. There is a temptation to treat the unknown as chaotic, as something beyond reason. But black holes do not represent chaos. They represent regions where our current descriptions stop, not where order disappears. The fact that we can predict the size of an event horizon, the luminosity of an accretion disk, and the gravitational influence of an object 10 billion light-years away is evidence of profound regularity. Ignorance, in this context, is temporary. The history of science is filled with boundaries that once seemed absolute. The atom was once thought indivisible. Time was once assumed to flow identically everywhere. Space was once believed to be a passive stage rather than an active participant in physics. Each boundary eventually gave way to deeper understanding. Black holes may represent the next such boundary. TON 618. With its immense mass and ancient light, sits precisely at that frontier. It is not an obstacle to knowledge, but a marker of where knowledge is being built next. There is also an emotional dimension to this story, even if it is rarely acknowledged. Awe is not separate from understanding. It is often the first step toward it. When confronted with scales that dwarf human experience, the mind is forced to let go of parochial assumptions. Priorities shift. Perspectives widen. TON 618 induces this effect almost effortlessly. It makes everyday concerns feel small. Not because they lack importance, but because importance itself becomes contextual. What matters at one scale may be invisible at another. Human lives are brief. Civilizations are fragile. Yet meaning is not erased by scale. It is defined within it. This is a lesson the universe teaches repeatedly. Stars live for millions or billions of years, yet their deaths seed space with them. Elements necessary for planets and life. Galaxies evolve over cosmic timescales, yet they are shaped by the collective actions of individual stars and clouds of gas. Black holes persist far longer. Still, yet they depend on their surroundings to grow and shine. Nothing exists in isolation. TON 618 may appear solitary, but it is the product of countless interactions, collapsing gas clouds, merging galaxies, turbulent accretion flows, and feedback processes playing out over billions of years. Its existence encodes the history of its environment. In this sense, it is a cosmic fossil. Just as paleontologists reconstruct ancient ecosystems from bones embedded in rock, astronomers reconstruct early cosmic conditions from objects like this. The mass of the black hole, the luminosity of the quasar, the composition of surrounding gas, all preserve information about a time when the universe was fundamentally different. This is why such objects matter. They allow us to test whether our understanding of cosmic history is consistent. They constrain models. They rule out possibilities. They force theories to align with reality. And sometimes, they surprise us. Ton 618 was not predicted in detail before it was observed. Its sheer scale exceeded expectations. It required revisions to growth models and motivated new ideas about black hole formation. It reminded astronomers that the universe often operates closer to theoretical limits than anticipated. This tendency toward extremes is a recurring theme. Stars approach the maximum mass allowed before radiation pressure halts further growth. Neutron stars approach the maximum density allowed before collapsing into black holes. Black holes themselves may approach upper limits set by feedback and accretion physics. The universe seems to explore the full range of what is possible. Ton 618 sits near one of those edges. That edge is not a cliff, but a gradient. Beyond it, objects become rarer, not impossible. Discovering whether even larger black holes exist is an ongoing effort. Each new survey pushes deeper. Each new instrument extends reach. And with each discovery, the context changes. What once seemed exceptional becomes part of a broader pattern. What once felt incomprehensible becomes simply extreme. This gradual normalization of the extraordinary is one of science's quiet triumphs. It does not diminish wonder. It refines it. Wonder rooted in mystery alone fades. Wonder grounded in understanding endures. Ton 618 offers that enduring kind of wonder. It invites us to think not just about size, but about time. Not just about power, but about process. Not just about darkness, but about the light produced at the edge of disappearance. And in doing so, it reinforces a deeper truth. The universe is not obligated to be simple. But it is consistent enough to be known. That consistency is what allows a species on a small planet, orbiting an ordinary star, in an unremarkable galaxy, to reconstruct the life story of a black hole billions of light years away. This is not inevitable. It is the result of curiosity, sustained across generations, of questions asked, refined, and passed on, of instruments built, improved, and shared, of ideas tested, discarded, and replaced. Ton 618 is part of that human story. Now. Not because it interacts with us in any direct way, but because we have chosen to pay attention. And as long as we continue to look outward, to question, to measure, and to imagine, objects like this will continue to shape how we understand our place in the vast architecture of reality. The universe does not speak. But through objects like TON 618, it leaves traces. And we are learning how to listen. Listening to the universe does not mean expecting answers in words. It means learning to interpret patterns, to recognize consistency, and to accept that some truths reveal themselves only indirectly. Ton 618 never announces its presence. It does not send a signal meant to be understood. It simply exists, obeying gravity, radiating energy, shaping its surroundings. Meaning emerges not from intention, but from interpretation. This distinction is subtle, yet profound. Human stories are built around agency. Characters make choices. Events have motives. Causes lead to consequences through decisions. The universe does not operate this way. Its stories unfold without awareness. And yet, those stories are no less rich. Ton 618 has no purpose. And yet, Its existence informs us about the nature of matter, energy, time, and space. It reveals how structures form, how limits arise, and how complexity emerges from simple laws applied relentlessly over vast scales. In that sense, meaning is not embedded in the universe. It is extracted from it. This extraction is an act of translation. We take raw data, photons collected by detectors, and convert them into models, narratives, and understanding. We impose coherence not by inventing it, but by recognizing it where it already exists. Ton 618 becomes meaningful because it fits into a broader framework. It fits into the story of cosmic inflation and structure formation. Into the story of the first stars and galaxies. Into the story of feedback, regulation, and equilibrium. Into the story of gravity as the dominant architect on large scales. Without that framework, it would remain just a bright point in the sky. With it, it becomes a chapter. There is also a temporal asymmetry embedded in this story. We can look back 10 billion years and reconstruct what happened. But we cannot look forward with the same clarity. The future of TON 618 is largely inferred, not observed. We project based on known laws, but uncertainty grows with time. Eventually, the black hole will fade into invisibility. Its accretion disk will thin. Its quasar phase will end. It will become dynamically quiet, interacting weakly with its surroundings except through gravity. For most of its remaining existence, it will be dark. In that darkness, it will persist. While stars burn out, while galaxies drift apart due to cosmic expansion, while the universe grows colder and emptier, the black hole will remain. It will orbit within whatever gravitational structures still bind matter together. It will slowly gain or lose mass through rare interactions and imperceptible evaporation. From the standpoint of cosmic time, this is stability. Ton 618 is not dramatic for most of its life. Its brilliance is brief. Its quiet endurance is long. This mirrors a broader pattern. Violence and intensity often define formative moments. But persistence defines outcomes. The universe's most energetic events are fleeting. Its most influential structures are those that endure. Black holes endure. This endurance makes them anchors of cosmic evolution. They provide continuity across epochs. They connect the early universe to the far future. They persist through transitions that erase most other structures. Ton 618 is one such anchor. And yet, endurance alone does not confer centrality. The universe does not revolve around black holes. They are participants, not rulers. Their influence is vast locally, but limited globally. Even the largest black hole affects only a finite region of space. Beyond that region, the universe continues largely unchanged. This balance between influence and limitation is another recurring theme. No object, no matter how massive, dominates everything. Gravity weakens with distance. Expansion reshapes large-scale structure. Even the most extreme entities are constrained by law. Ton 618 is powerful, but not omnipotent. Recognizing this prevents mythology from overtaking understanding. Black holes are not gateways to other universes, at least not in any testable sense. They are not cosmic vacuum cleaners. They are not engines of destruction sweeping through space. They are regions where gravity has reached an extreme, nothing more and nothing less. Their mystery lies not in supernatural behavior, but in the depth of physical law they reveal. This clarity matters. It allows wonder to coexist with rigor. It allows imagination to be guided rather than unmoored. It allows the story of TON 618 to remain grounded, even as it stretches. Intuition. Grounded wonder is sustainable. It invites continued inquiry rather than final answers. An inquiry is where this story ultimately leads. Every observation of TON 618 raises new questions. Every measurement tightens constraints while opening new uncertainties. Every theoretical advance clarifies some aspects while complicating others. This is not failure. It is progress. Science does not aim to eliminate mystery. It aims to relocate it, to push it from the familiar into the deeper structure of reality. TON 618 has already served this role. It has pushed mystery away from whether such objects exist, toward how they form, how they interact, and how they fit into a unified description of nature. That shift is subtle, but it marks genuine advancement. We now know that the universe can produce black holes of this scale. We know roughly when and how they form. We know how they shine and how they fade. We know how they influence galaxies and regulate growth. What we do not yet know is how all these pieces fit into a complete theory that spans from quantum scales to cosmic ones. That gap remains. And perhaps it always will. But even if it does, the pursuit itself has value. Because in trying to understand objects like TON 618, we refine our tools, sharpen our concepts, and expand our capacity for abstraction. We learn how to think across scales that no single lifetime can experience. In doing so, we become participants in a story far larger than ourselves. Not as central characters, but as observers, who have learned, improbably, to read the universe's traces and turn them into understanding. And that, in its own quiet way, is extraordinary. Extraordinary not because it was guaranteed, but because it was possible at all. There is no requirement in the laws of physics that the universe must produce beings capable of reflection. Stars could have formed and burned without ever giving rise to consciousness. Galaxies could have merged and dispersed without ever being observed. Black holes could have grown and faded without their stories being told. And yet, here we are. The same universe that produced TON 618 also produced the conditions that allow a small species to ask why it exists, how it formed, and what surrounds it. That parallel is not mystical. It is causal. Heavy elements forged in stars made planets possible. Stable stars allowed time for complexity to emerge. Physical laws remained consistent long enough for learning to accumulate. TON 618 is part of that chain. Its existence tells us that gravity is powerful, but also predictable. That matter can organize itself into extreme structures without collapsing into chaos. That the universe is not fragile, but robust across immense ranges of scale. This robustness is easy to overlook. We often focus on fine-tuning, on how slight changes to physical constants might have produced a very different universe. But what TON 618 demonstrates is not delicacy, but tolerance. Within the same set of laws, reality supports stars, planets, life, and black holes tens of billions of times the mass of the Sun. That breadth matters. It suggests that understanding is not confined to narrow conditions. That explanation does not break down when scale increases. That curiosity can be rewarded even when directed at the most distant and extreme phenomena. In practical terms, this means that studying objects like TON 618 feeds back into our understanding of everything else. Accretion physics developed to explain quasars informs models of star formation. Feedback mechanisms explored in galaxies help explain planetary atmospheres and stellar winds. Techniques developed to analyze faint cosmic signals improve medical imaging, communications, and computation. Knowledge propagates. The story of TON 618 does not remain in astronomy. It diffuses outward, shaping how we model complex systems, how we think about limits, and how we approach the unknown. There is also a temporal humility embedded in this story. We observe TON 618 at one moment in its long existence. That moment happens to be when it was bright enough to be noticed across the universe. Had we existed earlier, the quasar might not yet have ignited. Had we existed later, it might already have faded into darkness. Our window is narrow. Much of reality occurs outside it. This does not diminish the value of observation. It sharpens it. It reminds us that what we see is contingent, not complete. That absence of evidence is not evidence of absence. That many phenomena may have existed, or may exist now, beyond our ability to detect them. Ton 618 is visible because it cooperates with our instruments. There may be other objects equally extreme that remain hidden because they do not. This uncertainty is not a flaw in science. It is an intrinsic feature of inquiry in a vast universe. We work with fragments. From those fragments, we build coherence. That coherence is provisional, always subject to revision. Yet increasingly refined. Each generation inherits a framework that is more complete than the last, even as new questions emerge. Ton 618 entered that framework as a surprise. Over time, it became a constraint. Then a benchmark. Now it is a reference point, an object against which theories are tested and calibrated. Its role has evolved. So has ours. Early astronomers could only catalog points of light. Modern astronomers infer masses, spins, environments, and histories. Future astronomers may probe even deeper, perhaps finding signatures of quantum gravity or new physics. Encoded in extreme objects. Ton 618 will remain relevant across these stages. Not because it changes, but because our understanding of it does. This is another quiet truth. Objects do not gain meaning over time. Our interpretations do. Ton 618 has always been what it is. It has always followed the same physical laws. What has changed is the capacity of minds to extract structure from its behavior. In that sense, progress is not about reaching an endpoint. It is about increasing resolution. Each new layer of understanding reveals finer detail. New regularities. New limits. New connections. The picture never becomes final, but it becomes richer. This richness is what sustains long inquiry. It is why the story of TON 618 can be told not once, but repeatedly. Each time with greater nuance. It is why a single object can support hours of reflection without being exhausted. Because it sits at the intersection of so many themes, gravity and time, scale and meaning, darkness and illumination, endurance and change. Few objects encapsulate these themes so cleanly. In the distant future, long after the quasar phase of TON 618 has faded from view, its influence will persist indirectly. In simulations. In equations. In textbooks. In the conceptual scaffolding that future minds use to understand the universe. Its photons will have passed by then. But its imprint will remain. That imprint is not physical. It is informational. And information, once integrated into understanding, becomes part of the ongoing human conversation with reality. A conversation that has no final answer. Only deeper questions. And perhaps that is the most fitting conclusion to the story of an object defined by an event horizon, a boundary beyond which answers cannot return. Ton 618 reminds us that knowledge always has horizons. But it also reminds us that approaching those horizons is itself worthwhile. Not to conquer them, but to understand where they are, and why they exist. And in doing so, to better understand ourselves. Understanding ourselves through the universe is not an act of projection. It is an act of alignment. We do not impose meaning onto TON 618, we discover where our capacity for meaning intersects with structures that exist independently of us. That intersection is fragile. It exists only because certain conditions are met, stable laws of physics, sufficient time for complexity to arise, and minds capable of abstraction. Remove any one of these, and the story dissolves. Ton 618 does not need us. But the fact that we can know it tells us something essential about the universe we inhabit. It is a universe that allows distance without disconnection. A universe where causality stretches across billions of light years. A universe where events that occurred before our planet formed can still influence what we think, imagine, and understand today. This continuity is not guaranteed in all conceivable universes. Some possible universes would expand too rapidly for structures to form. Others would collapse too quickly. Some would be dominated by chaos, others by uniformity. The universe we observe occupies a narrow path between these extremes, a path that permits both immense structures like TON 618 and localized complexity like life. This balance is not evidence of design. It is evidence of constraint. The laws of physics limit what can exist, but within those limits, they allow remarkable diversity. Ton 618 represents one extreme outcome within those constraints. We represent another. Neither is privileged. Both are consequences. Seen this way, the story of TON 618 becomes less about awe at size and more about coherence across scales. The same gravitational constant that governs falling apples governs the growth of ultramassive black holes. The same quantum processes that shape atomic behavior influence the opacity of accretion disks. The same thermodynamic principles that limit engines constrain how matter spirals into darkness. There is no separation between the everyday and the cosmic. Only difference in scale. This realization erodes a common misconception, that the universe becomes fundamentally different as it becomes larger. In reality, it becomes more revealing. Extremes strip away approximations and expose underlying principles more clearly. Ton 618 does this relentlessly. It forces gravity into dominance. It pushes accretion to near its theoretical limits. It amplifies feedback processes until their consequences become unavoidable. In doing so, it clarifies what is essential and what is incidental. This is why extreme objects are so valuable. Scientifically, they simplify by exaggeration. And yet, simplification does not make them simple. Ton 618 remains a deeply complex system, involving plasma physics, magnetohydrodynamics, radiation transfer, relativistic effects, and cosmological context. Understanding it requires synthesis across disciplines. No single equation captures it fully. This complexity mirrors the universe itself. Not complicated in the sense of randomness, but layered. Each layer obeys its own effective rules while remaining grounded in deeper ones. Progress comes from learning how layers connect. Ton 618 sits at the intersection of many such layers. It connects stellar evolution to galaxy formation, local physics to cosmological expansion, classical gravity to quantum uncertainty, observation to theory. Few objects span such a range. That span makes it uniquely powerful as a narrative anchor. Not because it is dramatic in a cinematic sense, but because it is integrative. It gathers threads that might otherwise seem unrelated and binds them into a coherent picture. And coherence, more than spectacle, is what sustains long reflection. Spectacle fades. Coherence deepens. As the story of TON 618 stretches across hours of narration, what remains is not shock at its mass or size, but appreciation for the processes that made it inevitable once. Conditions aligned. This appreciation transforms fear into curiosity. Black holes often inspire anxiety. They are portrayed as devourers, as threats, as symbols of annihilation. But viewed through the lens of physics, they are not hostile. They are indifferent. Their behavior is predictable. Their influence is local. Ton 618 will never affect Earth. Its radiation faded long before our planet existed. Its gravity cannot reach us. Its future is decoupled from ours. And yet, intellectually, it reaches us. It shapes how we think about limits, endurance, and scale. It challenges us to refine our tools and expand our imagination without abandoning rigor. This is a healthier relationship with the unknown. Not one of fear, but one of engagement. Engagement does not require answers to every question. It requires respect for complexity and patience with uncertainty. Ton 618 rewards both. As we approach the end of this long reflection, one truth becomes clear. The value of studying objects like TON 618 does not lie solely in what they tell us about black holes. It lies in what they teach us about inquiry itself. They show us that understanding is incremental. That extremes clarify fundamentals. That mystery is not a barrier, but a boundary that gives direction to thought. They remind us that the universe is not obliged to be comprehensible, but that, remarkably, it often is. And perhaps that is the quiet conclusion toward which this entire story has been moving. Not toward the black hole, but toward the realization that knowledge is a relationship. A relationship between mind and cosmos. Between question and constraint. Between what can be known and what must, for now, remain just beyond the horizon. Ton 618 marks one such horizon. Not as an end point, but as a place where understanding pauses, reflects, and prepares to go further. And as long as that pause continues, thoughtful, curious, and humble, the story does not truly end. And so the light fades. Not suddenly, not violently, but gently, stretched thin by time and distance, diluted by the expansion of the universe itself. The photons that once blazed outward from a furious accretion disk, brighter than entire galaxies, arrive here as whispers. Faint signals captured by mirrors and sensors, interpreted by minds that did not exist when that light began its journey. The black hole that powered that brilliance remains. Silent now. Immense. Patient. Ton 618 no longer announces itself with overwhelming light. Its quasar phase has likely ended. The surrounding gas has thinned. Star formation in its host galaxy has slowed. What remains is a massive, dormant black hole, carrying within it the accumulated history of billions of years of cosmic evolution. It does not mark the center of anything. It does not command the universe. It simply persists. And in that persistence lies its final lesson. The universe is not defined by moments of violence or brilliance, but by what endures after them. Stars burn brightly and fade. Galaxies collide and settle. Civilizations rise and vanish. Even the most luminous objects spend most of their existence in quiet stability. Black holes embody this truth more clearly than anything else we know. They are born in chaos, grow through intensity, and then remain, largely unchanged, while everything around them evolves. They are not symbols of destruction, but of continuity. Ton 618 has already outlived countless stars. It will outlive countless more. Long after galaxies grow dark and space stretches thin, it will still exist, slowly and almost imperceptibly losing mass over timescales so vast they defy imagination. And yet, despite its permanence, it is not the point. The point is that we were able to know it. That beings confined to a small planet, orbiting an ordinary star, could reconstruct the story of something so distant, so ancient, and so extreme. That we could trace the fingerprints of gravity and light across 10 billion years and turn them into understanding. This is not about dominance over nature. It is about participation in it. Ton 618 does not care that it has been observed, measured, or named. The universe does not require recognition. Meaning does not exist out there, waiting to be found. Meaning arises here. In the act of looking outward and thinking deeply. In the decision to follow faint light to its source. In the patience to accept uncertainty without surrendering curiosity. The black hole remains, indifferent and unmoved. But something has changed. We have expanded our sense of scale. We have stretched our understanding of time. We have learned that the same laws that govern our everyday lives also sculpt the largest structures in existence. We have seen that the universe is not hostile to understanding, only demanding. And perhaps that is enough. Because in the end, the story of TON 618 is not a story about darkness. It is a story about light, traveling across unimaginable distances, surviving impossible odds. Carrying with it the quiet message that the universe, in all its vastness, can still be understood. And as long as we continue to listen, to question, and to wonder, that message will never truly fade.